Welcome to the Deep Dive, the place where we distill years of technical knowledge and some really surprising insights from a stack of sources down to the essential practical truth. Our mission today is a big one. We want to make you fluent in the fundamental concepts powering what is, really, the fourth great technical revolution of our lifetime. We're launching a deep dive into applied machine learning and AI for engineers. And if you've been through the shifts from the personal computer, the internet, and then the smartphone, you know that ML and AI are having just as profound an impact. We've drawn on specialized guides, technical sources, all designed to solve real business problems, the kind that you just can't crack with traditional algorithms. Our goal is for you to understand not just what ML and AI do, but how they actually work under the hood. Just how powerful is this? My personal introduction came years ago with a phone call from my credit card company. They flagged a fraudulent $700 purchase for a necklace in a city I hadn't visited in years. And the impressive part wasn't just the detection. I mean, I'd use that card all over the world. It was that they knew somehow that this specific transaction wasn't me. And yet sometimes they'd flag a purchase I made 2 miles from my house. It was clear this wasn't some simple rule. It was something more powerful than a mere algorithm.
And that's it, right there. That dynamic nature is the core concept we need to unpack. Machine learning is fundamentally about finding patterns in massive data sets, which are really just mountains of ones and zeros, and then using those patterns to make predictions. The concept itself is pretty intuitive, but the jargon often gets in the way. Our job is to cut through that noise.
Okay, let's start right there then. What is the dividing line between that old school programming and machine learning? Where does the code stop and the learning, begin?
Well, in traditional programming, you, the engineer, provide all the explicit rules.
The if-then statements.
Exactly. If the purchase is over $500 and it's outside the country, flag it. You build the logic tree, and that logic is fixed until you go in and change it.
Okay, so it's explicit, dictated by the programmer.
But machine learning flips that on its head. You don't write the rules.
So what do you provide?
You provide the inputs and the answers, what we call labeled data. And then these special learning algorithms, they fit a mathematical model to that data during a process we call
training. Training, exactly. The model figures out the relationship itself. To tell cats from dogs, you don't code whisker length. You just show it thousands of cat and dog photos, and it learns.
So the model is learning from observation, not from instruction. That's a huge paradigm shift.
It is, and its success depends entirely on the data. So every data set has two key parts, the feature columns, which is your input data.
Like transaction amount, time of day, distance from home, that sort of thing.
Right. And then you have the label column.
Which is the answer you want, fraudulent or legitimate.
No, precisely. Now, this is where it gets sophisticated. Including transaction amount is easy, but what about, say, the difference between this transaction and the user's average spending?
Or the speed of their spending in the last hour.
Yes. You're talking about feature engineering.
Creating new, more powerful features from the raw data.
And that is arguably the highest leverage activity in all of machine learning. The features you engineer define the ceiling for your model's performance. It's how you turn raw data into a truly predictive asset. The model's only as smart as the information you organize for it. Makes perfect sense. Okay, so that brings us to the first major architectural split in ML supervised versus unsupervised learning.
Let's start with unsupervised. This is where the system shines by figuring out patterns all on its own, because you don't actually need to label the data. You use it when you don't know the answer yet. And the most popular technique here is called k-means clustering. The goal is really simple. You group similar data points together into a number of clusters, let's call it AMV, that you specify.
So the system is just finding the natural groupings in the data.
Yeah.
What's a really high value business use for that?
Oh, without a doubt. Customer segmentation. Imagine you have a huge customer data set, annual income, how often they buy, a spending score you've calculated.
Okay.
K-means will automatically find the distinct groups for you. The frugal high earners, the impulsive low-income shoppers, groups you might never have seen just by staring at a spreadsheet.
That is powerful. But it raises a technical question. How do you know the right number of clusters? How do you pick MM? You can't just guess.
You can't. And this is where we use a bit of math to help our intuition. It's called the elbow method. You basically plot the inertia, which is a measure of how tight the clusters are, against the number of clusters you're testing.
And you're looking for an elbow in the graph.
Exactly. As you add more clusters, the inertia always goes down. But at some point, adding another cluster gives you diminishing returns. The curve flattens out.
And that sharp bend, that elbow, is your sweet spot.
That's your mathematically optimal number of clusters. It's the perfect balance.
It's a great way to make sure the results are statistically robust, not just arbitrary.
Absolutely. And these insights can completely change how a business operates. I saw a great example in a sales organization. An analyst used K-means on their lead pipeline data, and the clusters revealed that the number one reason a lead failed wasn't price.
What was it?
It was just the time it took for a salesperson to make that first contact. That one insight, pulled from an unsupervised pattern, led directly to workflow automation that drove a huge improvement.
Wow. Okay, now let's shift to supervised learning. This is what we need for problems like fraud detection, where we have all those labeled examples. And we know this breaks down into regression for predicting numbers, like a home price, and classification for predicting categories.
Right. And for classification, a really simple place to start is K nearest neighbors, or KNN. The idea is super intuitive. To classify a new point, you just look at its, say, nearest neighbors in the data, and you let them vote on the new point's label.
It's basically guilt by association, using proximity to determine identity.
Exactly. If you're classifying an iris flower, you just find the known flowers with the most similar petal and sepal measurements and see what species they are.
But for something big and complex like fraud detection or, say, predicting Titanic survival, we need more powerful models. I'm guessing that takes us to logistic regression.
Yes. Logistic regression, or LR, is the workhorse for binary classification problems with just two outcomes. It's fast, it's simple, it's easy to interpret. And while it's inherently binary, libraries like scikit-learn have clever ways to extend it to multi-class problems, using strategies like one versus rest.
That efficiency is key. But before any of this, we have to prepare the data. The 90% of the job that isn't the fun part.
The necessary drudgery. Since ML only understands numbers, we have to encode any text data. The simplest way is label encoding. You just replace male with a 1 and female with a 0.
That seems fine for gender. But what if I'm encoding, say, colors, red, green, and blue? If I use 0, 1, and 2, what's the mistake there? Does that just slow things down, or is it worse?
It's much worse. It fundamentally misleads the model.
Wow.
The model sees those numbers and it assumes an order or relationship that doesn't exist. It thinks blue 2 is somehow twice as much as green 1. It's an artificial weighting that can completely ruin your results.
Okay, so that brings us to the better way.
One-hot encoding. This solves that problem by adding a new column for each unique value. So instead of one color column, you get a colored column, a color green, a color blue, and the value is just a 1 or a 0. Every category is treated equally.
Right? Data is clean, it's numerical. Now we have to test the model. We can't use our training data for that, can we? The model's already seen the answers.
Absolutely vital. You have to hold back a separate test set to see if the model can generalize, if it can make accurate predictions on new data it's never seen before.
And this is especially tricky with imbalanced data, like the fraud example. If only 0.2% of transactions are fraud.
Right. A lazy model could just predict legitimate every time and be 99.8% accurate.
But it would be completely useless. So that simple accuracy score is not enough.
Not at all. This is where we need more nuanced metrics. We have to define the cost of being wrong. First, there's precision. Precision penalizes false positives.
So incorrectly flagging a good transaction as fraud, you're annoying your customer.
Exactly. If you prioritize precision, you're saying, don't bother the customer unless you're really, really sure.
And the other side of that coin is recall or sensitivity.
Recall penalizes false negatives. This is when the model says a transaction is fine, but it was actually fraud.
When you really don't want to miss.
Right. So for fraud, or for medical diagnoses, the cost of a false negative is catastrophic. You let a tumor go undetected, you let fraud through. You have to optimize for recall.
Whereas for something like a spam filter, you'd probably care more about precision. Blocking an important email is way worse than letting one piece of spam through.
Precisely. Understanding that trade-off is the difference between a successful project and a failed one.
Let's turn to complexity. What happens when you have a data set with hundreds, even thousands of features? You mentioned one of the minor miracles of machine learning. That's PCA. Wait, you're saying we can throw away 90% of our data columns and still keep 90% of the information? Sounds like a magic trick.
It does sound like it, but it's a very real dimensionality reduction technique. PCA doesn't just drop columns. It finds new, combined features, principal components that capture the most information, the most variance in your data. It mathematically compresses it. And it has some amazing applications. First, data anonymization. This is how they were able to release that big credit card fraud dataset. The features, V1 through V28, were principal components.
Ah, so you can share the data for research without revealing the secret sauce, the actual metrics the bank is using.
Exactly, protecting IP. The second big use is visualizing high-dimensional data. If you have data on handwritten digits, that might be 64 dimensions. PCA can crush that down to just 2.
So you can actually plot it on a 2D chart and see how the different digits cluster and separate.
We can literally see the boundaries. It makes the incomprehensible visible.
Okay, this is a great foundation. But now we get to the really interesting part, deep learning. This is where traditional algorithms hit a wall, right? With unstructured data like images, audio, text. This is what powers modern AI.
Right. And the deep part just means a neural network with many, many hidden layers. But the real breakthrough, especially for images, came from convolutional neural networks, or CNNs. CNNs are so powerful because they treat images as images, not just a flat list of pixels. They use these things called convolution kernels.
These are like filters.
Think of them exactly like filters. One kernel might learn to detect vertical edges, another learns to find curves, another a specific texture.
And the model learns which filters matter during training.
Precisely. It uses these kernels to pick out low-level features, the shape of a dog's ear, and then deeper layers in the network combine those into more abstract concepts, like dog.
But training a state-of-the-art CNN from scratch takes millions of images and huge amounts of computing power. That sounds totally out of reach for most engineers.
It is, which is why transfer learning is probably the most important practical shortcut in modern AI. The big tech companies, they spend the millions to train these huge models on massive data sets like ImageNet.
Which has thousands of categories, Arctic foxes, polar bears, everything.
So what you do is you take one of these pre-trained models and you just strip off the final classification layers, the part that actually says Arctic fox.
And what's left is the valuable part.
What's left are the bottleneck layers. These layers have become world-class experts at extracting meaningful features from any image. So you just run your small, specific data set, maybe a few hundred images of defective parts off an assembly line, through those bottleneck layers to get expert features. Then you only have to train a tiny new classifier on top of that.
The efficiency gain must be incredible.
Orders of magnitude faster. You're not retraining the whole network, just the very last piece. And the results are stunning. We've seen a CNN trained on wildlife suddenly be able to identify a walrus, even though it never saw one in training, just because its understanding of shape and texture was already so sophisticated.
And it's not just for pictures. You mentioned using this for audio.
Yes, you can convert audio into a spectrogram, which is basically a picture of the sound's frequencies over time.
And then feed that image into the CNN.
And suddenly, the network's visual expertise can be used to classify sounds. People are using this right now to detect illegal logging in rainforest by classifying the sound of a chainsaw or a truck engine. It's an amazing application.
So let's bring this all back for the listener. We've gone from finding hidden customer segments with K-means, to balancing the costs of being wrong with recall and precision, to protecting IP with PCA, and now harnessing these giant models with transfer learning.
The main takeaway is that the tools to do this, scikit-learn, TensorFlow, Keras, are incredibly accessible. The barrier isn't really the coding anymore. It's understanding these core concepts so you can pick the right tool for the job and avoid the common pitfalls.
Which leaves us with a final provocative thought for you to consider. We know that credit card fraud system used PCA to anonymize its features, V1 through V28. If you were the engineer trying to make that model even better, what new features about the user, their age, their income, their recent purchase history would you create? And more importantly, how would the model learn to use the relationships between your new custom features and those existing anonymized PCA features to make an even smarter decision about that one unusual purchase just 2 miles from home? Keep that idea of finding signals in those relationships in mind as you explore this further.